Let's see.
So the master set is the 24.
Yes. As can clearly be seen in that piece of paper on the wall.
No,
I'm going to pretend it can be easily seen. So we got Ronald, John, Adam, Selena.
Is there a master set for every chapter?
In theory. I haven't done all the master sets. That's something that I've done for the other classes, and this is the first time I've done it for 133. So, right now there's chapter 13. I suspect time's going to get away from me, and at some point the master sets will drop off. But for right now, that's the plan. Any questions on the homework problems right now?
I'll put down the lab dependent clause on the Y.
While you're doing that, let me see if I think my textbook is here. That's the So Ronald, you're about to come up with a question?
Well, me? Not at the moment.
Okay.
I'm writing some details for the lab in my book.
Okay.
Because the dependent clause is the
Dependent
displacement and the force is the independent clause.
Variable.
Variable. Well, they say independent in the book.
Yep. You know, my dad was an English teacher. Independent, dependent clauses, something I heard a lot. Yeah, he corrected my grammar all my life.
So I need to write that down so I get the X and Y's together.
Pardon?
Independent clause like from English?
Yeah, when I hear independent clause, yeah, I think English.
So you was an excellent English person in your household.
My writing style in English was that of someone who did science and math. There's a whole lot of subject, verb, object, subject, verb, object.
Agreement.
Well, I had the agreement down. That part was fine, but it was the flow, the prose, which made it sound beautiful. That was not my thing.
Very logical.
Yeah. I like diagramming sentences, which I suspect that at least 3 of you have never done.
Yeah, I don't know what that is. Well, I mean, I probably do know what that is, but I don't. It's been a long time since I.
If you ask your parents, I suspect your parents all did diagramming sentences at some point. It's out of favor right now, but people either really liked it or really hated it. I don't think there are a lot of people in the middle. When I taught elementary school, I thought, I'm going to do diagramming sentences with these kids. And I mentioned it in class, or I mentioned it during a parents' night, and some of those teachers, some of the parents were like, oh no.
Okay.
Actually, the one who I rolled the most was the one whose kid loved it the most. Yeah, they have that kind of kid. Anyway, one last question, one more time, any questions at the moment? All right, so let's take this idea. Oh, one thing I did notice when I was looking at the video from Monday is that I was off screen too much of it. So this side I'm good on. Over there, just past the black marker. Somewhere around there. And I estimate I lost about a half hour of video from Tuesday. So we did this in the previous chapter. This is Hooke's law.
Force.
The fact that the force that a medium will exert is
Change on this.
directly proportional to the negative of how far it's been displaced. And the negative just means the opposite direction. So if I stretch something that some material, if I stretch a material, the material wants to come back to its equilibrium position, or if I compress a material, it will want to push out to some position. So based upon Newton's second law, so let's take the idea of the slinky here. Let's assume it's ideal. I have some mass on the end, I pull it down, I let go, and the thing oscillates back and forth. So based upon, or what is Newton's second law anyway?
Object will stay in motion until another object.
That's the third one.
God dang it.
Oh, sorry, I apologize, that's the first one.
Oh boy.
This is the math equation.
Oh.
Y equals mx plus b.
I'll agree with the M.
Time.
I don't know.
E equals mc squared.
That's
I'm thinking-
Einstein.
You could get there from Newton's second law, but that's
That's
but once you've had the calculus, that's a 3-hour talk right there. I'm not going to subject you to that, don't worry. F equals,
MA.
that helps a few bars. All right. Newton's second law, I will abbreviate it as N to L for the few times that we actually need it. While we're here, since we've already talked about first and second, what's the third law?
Third law is every reaction has an equal opposite reaction, and first law is an object in motion stay in motion.
Or object at rest will stay at rest. The first law is actually just the wording of this. An object is basically going to keep doing whatever it's doing unless there's some force that causes it to change. This is it. The exact same thing in math form. All right, so I have an equation here, and if I stick MA in there, this becomes MA is equal to negative K delta X. I got two vectors here. I have acceleration and displacement. What's the relationship between, let's go for the goal. What's the relationship between acceleration and displacement?
Proportional.
In this particular case, yes. In general, what's the relationship?
They are linear.
acceleration causes displacement.
Yeah, I think you could do a cause and effect there. It's looking for more math wise here, but I mean, not wrong. You would say the linear relationship at first.
Yeah.
It's actually not a linear relationship in this particular case.
Quadratic.
It is not a quadratic either.
Well, they're proportional, but
I'll agree with they're proportional. Oh, I apologize. Acceleration does have a linear relationship with displacement. However, the function for acceleration is not linear. We'll get to it. What's the relationship between velocity and position? Or how would you find velocity?
The distance traveled over a period of time.
That would be speed.
In a direction.
Acceleration to a certain direction.
Say it again?
Acceleration towards a direction.
What, for velocity?
Yeah.
I'm going to go with no. Acceleration and velocity are related to each other, but they can't be used as interchangeably as you just said. All right, what's acceleration?
Change in velocity.
Are you stopping there?
Is there?
There's more.
There more?
Change in velocity and acceleration are very much related to each other, but they are not the same thing.
Relative to 0.
The speed.
You probably could make an argument for that, not where I was going. Because speed, how fast you're going always is relative to something. There is no absolute reference frame which is going 0. All right. We have some major, let's take a look at some of those things that, and by the way, every semester I go through this just to try to figure out what people remember from 131.
No.
And yeah, pretty much everyone remembers the same stuff. So, but there's that hope springs eternal. All right, so position is what I'm using X for. I could use R, S, Y, Z. Those are the common ones to use for position. And we talked about last time that position is where an object is relative to the origin, or 0. You pick some reference point, and then position is just where you are relative to that.
Time has to be in there somewhere.
Displacement is where you are relative to, in essence, where you started. So just a quick example. Let's say that I've got a graph right here, and there's 0, and I'm starting at this point. Or I got a map of the US, and this is where I was born, and this is where I live right now. So we'll call that X of 1. And so my initial position is right there. And I can, once I've defined where my origin is, where 0 is, I can now give a location. I can give a position here based upon how far I am away and at what angle. So I got a direction and a magnitude. I then move over here. So this is my new position. We'll call it X2. And this vector going from where I started to where I ended, that's my displacement. So it's all a matter of difference between displacement and position is what you're choosing as your reference. Displacement traditionally is looking at where you started. Position looks at where you're setting 0 to be. A lot of textbooks will go ahead and just automatically assume that your starting point is always 0, and so they'll use displacement and position interchangeably. There is a difference there. So this is displacement, as talked about on Tuesday. Velocity. And I think people were getting to it. It is a vector. And so that would be speed in a particular direction.
Time has to go in there somewhere, right?
Yeah, and that's one of the things that was left off earlier from what John was saying.
What was left off?
And acceleration is the time rate of change of velocity. All right, so we've got just the beginning vocabulary for describing motion. All right, so velocity, when you said distance over time, that is speed, because distance does not care about direction. Velocity cares about direction. And so it's the change in position over the change in time, or displacement divided by time, but not distance. And then acceleration, change in velocity divided by time. So there is the time element related to acceleration. So if you're driving a car, what are the 3 things that you have easy access to as a driver that can change the velocity?
The brakes and the accelerator.
There's two of them.
Emergency brake.
I'm going to lump that under brake. If you want to include emergency brake as one of them, then there's 4.
The ignition switch.
The what switch?
The ignition switch. The key switch.
Oh. If your car's moving, can you actually, I guess some cars could do that.
And, the steering wheel? The steering wheel?
Steering wheel. Why is the steering wheel, how can the steering wheel cause velocity to change?
Because it gives you direction.
So the steering wheel is an accelerator from a physics point of view. All right, so we have this relationship here. So let's think about if I have a velocity time graph. Let's just make a simple velocity time graph. So I got velocity and time. And I want to figure out my acceleration. How would I do it? Or do you need numbers? Oh, all right. Let's make this times in seconds. So let's make this 4 seconds, and this is in meters per second. So let's make this 20, and it goes through the origin here.
So you have to have a vector, which that is.
There is a vector implied in this. Well, it's actually explicit. The fact that I'd say that this is velocity tells me that we're dealing with a vector. What is the direction that's given in this graph?
Positive.
Exactly. Now, I've given no context here, but this would be appropriate for a one-dimensional motion where an object's just moving along a line, and somewhere in the problem we've defined the positive direction. So, assuming that we are traveling in the positive direction, whatever that happens to be. If you need a context, I got a line right here, and I have a box that is sliding in that direction. Since it's speeding up, let's put it on a ramp. I have a box on a ramp, and it is speeding up in that direction. That's the direction of the velocity, and I'm going to say that is positive. How would you find the acceleration?
Usually 20 over 4.
Why?
Because, alright. Because if you're doing it relative to 0, 20 is your end point, 0 is your start point, 20 minus 0 is 20. And then same thing for time would be 4 minus 0, that gives you 20 over 5, or 20 over 4 is equal to 5.
And units?
It's going to be velocity meters per second, meters per second squared.
Absolutely. So as long as we're sticking with this international standard units, acceleration should always be meters per second squared, velocity will be meters per second, position displacement will be meters. Your textbook sometimes will get away from the standard international standard and just give US customary units. Just recognize what it's doing. So this 5, so now let's change it a little bit. I have a second car, like that. So it starts at 10. Or a second box on the ramp. What is its acceleration?
3 millimeters per second squared.
Wouldn't it be 5 meters per second squared again?
It would be.
Because it'd be 30 minus, or 10 minus 30.
Ooh.
Oh, sorry. 30 minus 10.
Yep. So for this one right here, 30 minus 10 over 4 minus 0, which is 20 over 4. So now to look at it from my questions up to here before I try to connect it with ultimately what we're going to be doing over there. All right. So from a math point of view, let's remove all context. You see a graph here, and you have these two lines looking like that. What can you say about those two lines? What's common to the two lines?
Parallel.
Parallel.
Okay.
They're proportional to each other.
They're the same.
The same, because they're 5.
Officially, they would not actually be proportional to each other, because if you're saying proportional, really what you're saying is if I take the value for one and multiply by the same number each time, I can get the value for the other. So the difference is some additive. There's some thing you add to it. So officially not proportional to each other. However,
Slope.
that's the word I was looking for. They have the same slope. Acceleration is the change in velocity over change in time. It is actually just from a math point of view, it is the slope of the velocity versus time graph. You still have a question?
No.
Okay. You had that look.
Looks is deceiving.
That's true. All right, velocity here is looking at the same structure, change in y over change in x, if you want to think it in terms of math brainwashing. But the change in position over change in time, this is just the slope of the position versus time graph. So the relationship here, in order to work this out, what I need to do is figure out what function for position can I do.